Hello all. Today we discuss about diode transistor logic. Using diode transistor logic, we design the various logic circuit like AND gate, NOT gate, etc. So first of all, look in this circuit. First circuit is known as our NOT gate circuit or inverter circuit. So now in this circuit, look in this circuit. This is a NOT gate circuit. Okay. So in this circuit, we looked at this is RC transistor. This is a normal or Schottky diode or normal diode. If you connect here Schottky diode, then this is known as Schottky transistor to make the first order operation and preventing from going into saturation mode. And this is the input. Here one diode is connected. The logic is when 0 apply here, then diode is forward biased, and here the voltage drop is 0.7 and the base emitter cut-in voltage is 0.7. That means there is a no base current is flowing. No base current means no collector current. No collector means there is a no drop. That means output equation is followed by this equation. So no collector current drop means this is part equal to 0. So output equal to get logic 1. And when we apply logic 1, then the diode is reverse biased. So here base current is flowing because here the high voltage appears 5 volt. Therefore base emitter is a cutoff. Sorry. Therefore base current is flowing and also collector current is flowing. Therefore across the RC the collector current is flowing and there will produce the voltage drop, and final output V0 equals to VC minus this drop, that means equal to 0 volt. So now it is seen that when we input logic 0, then output equal to 1, and when we put logic 1, then output equal to 0. So this is a DTL diode transistor based inverter circuit. Okay, now next NAND gate. What is a configuration of NAND gate? Just we connect here one extra Schottky diode or non-diode. So now when both input equal to 0, just follow this truth table. When both input equal to 0, then both diodes forward biased. So here the low voltage, therefore there is a no base current because here cut-in voltage 0.7. So no base current means no collector current. No collector current means there is a no voltage drop. Then output equal to 1. So this is same for the any kind of logic, any other logic 0 1 and 1 0, because 1 0 means one diode is in forward bias mode. But when both diode is 1 1, we apply input here both diode equal to 1 1, then transistor in this diode are reverse biased. Therefore here logic high is appear. Logic high means there is a base current flow because base emitter is a saturation mode. Okay. So now the collector current is flowing. So collector is now saturation mode. So now when collector current is a saturation, so therefore this drop IC into RC produced here. So now output equal to VCC minus IC into RC. That means this is equal to 0. Okay. So this is the logic of NAND operation. Now next is a diode transistor. In a diode transistor technology, look here that this part is the same as this circuit, because this is a transistor, the diode transistor based NAND gate, and here we connected just connected one inverter or one NOT gate to make NAND gate from AND gate operation. Okay, it's very easy because this is a single inverter operation. This is single inverter connected to the output. This inverter circuit is same as this inverter, but here we not connected any base resistance. Why? Because this output is connected to here. So just only the diode and the transistor to make the inverter operation, because this RC and the output stage of this circuit is drive to this stage. Okay, so that's why this circuit is not connected here. We just connected this part only. So this part is take action to invert our logic from 0 to 1 or 1 to 0 as corresponding for the corresponding inputs. Okay. Now this is the equivalent circuit of diode transistor logic. This is known as NOR gate. So this is the table of here two inputs are applied and this is output, and the logic state is this is 1, this is 0, this is 1 0, logic 0 also, and this is also logic 0. So here input A are applied, input B are applied. These two input, this is transistor 1 NOT gate and this is the transistor based. This is the diode connected from, this is RC connected to plus VC, and here this is RC RB, and here we just connected the RC and the diode from the collector to connected to the transistor collector of region. Okay, transistor collector point. So this is a P side and this is N side. So operations look like a when both input equal to 0. So this circuit is an inverter operation. So 0 means this output equal to logic 1, and when this circuit equal to 0, so therefore this is forward bias. This is forward bias means here voltage drop equal to 0.7. So transistor is cut off. That means there is a no current. that means here also produce the high voltage. So that's why here we getting the high voltage. But anyone taking action here, 0 1 or anyone, either these one 0 and these one, or these one is 0. What is the condition? This condition is when here we apply 1, then 1 means here diode is reverse biased and here appears high voltage. High voltage means their base is a base current is flowing and collector current is flowing. That means there is a voltage drop, and this is output equal to 0 volt, nearly tends to 0 volt. And these two are short circuited, so due to this low voltage the output is always low. Okay, so this is, and when see that when here we apply 1, okay, any one condition, either 1 0 or either 1 1, then this diode is reverse biased, and here we apply high voltage. High voltage means 5 volt. That means here base current is flowing. Base current is flowing means here collector current also flowing. So therefore here potential drop equal to IC into RC. That means this VC minus IC into RC, here 0 volt. So any 1 0 0 means the output goes to low. So this is for the NOR gate table. Okay, so how can you design OR gate? So it's very simple. Just we connected this output to this circuit. So this is the NOR gate we already discussed in the previous slide. So this is plus VC. Okay, so this is inverter. So from Y we get A or B operation. Okay, so this is our the connection point. So this is our DTL technologies using Schottky transistor methodologies, diode transistor methodologies. Now we design XOR gate. Okay, we already know that for XOR gate the output is Y is equals to A bar B plus AB bar. Okay, so what will be the output? The output is A XOR B. Okay, so using NAND gate the configuration is look like this. This is our configuration. This is the configuration of logic blocks. We also design using FPGA DTL. In my FPGA course lecture videos, please follow the XOR gate operation or NAND gate operation in VHDL language. So the output is, but in this lecture we only talk about the internal technology using diode transistor logic technology. Okay, so this is here connected 4 NAND gates. Everyone know that how the XOR gate is coming. In the previous video we show that these 4 NAND gate produce the output equal to XOR gate. Okay, so now here 4 NAND gate connection. So now 4 NAND gate using 1 NAND gate using DTL technology. We see in the previous slide this one resistance. Here one diode is connected. Here one resistance, and here we connected 2 Schottky diode. This is 2 Schottky diode connected. This is 1 Schottky diode. This is plus 5 volt. The input is A and B. Just consider that this AB is equal to this A and B, and the output of this NAND gate is connected to the another input. Okay, another input means here another NAND gate is connected. So just a minute. Sorry. Okay, we again draw this picture, same picture. So this is our another NAND gate. This is 1 Schottky diode, and this is another Schottky diode. This is short circuited. This is RC and this is RB. So now look here. These output is connected here, and these output equal to A, because this A is connected this input and this output is connected here. So this output is connected this input and A. That means this A is internally connected to this input. Okay. Now in the bottom part, again we draw the another NAND gate. Okay. is in the IC, built in the IC. But in today there is CMOS technology and TTL technology are used. Diode transistor is not used because there are so many disadvantages like a speed operation, like a propagation delay, etc. So now look here. Here one input is connected to B and another input connected to this output. So we connected these output to these here, and this B input is connected here. To reduce the complexity, I here just write B. That means this B and this B are internally short circuited. Okay. So now from these two output, now one output is coming from here and one output is coming from here. So from these two output, again one NAND gate is connected. So now again this is one NAND gate. Again we draw, this is Schottky transistor. Here we connected plus VC, and this is one in NAND gate. Okay, and one Schottky diode, because this is a 2 input NAND gate. This is the output, final output A XOR B. Okay, so now these output is connected here and these output coming from here. So student, please note that this is the technology of DTL, internal technology of XOR gate, to make XOR gate using DTL, diode transistor technology. Okay, this is very important. And how we implement this XOR gate? So this is very easy, because when we design XOR gate, we just connected one inverter across the output. That means in the previous slide I show it, that is, this is an inverter. Okay, so output equals to A XOR B, because if we invert operation of XOR, then we get the XOR output. Okay, or vice versa. So this is the DTL technology using XOR gate, designing using DTL technologies. Okay.